In previous lectures, we took solids as if they had no pores, no porosity. In this lecture, we're going to formally introduce porosity and how porous solids can have deformations that depend on the solid deformation itself, but also on the deformation of the pores. For example, here we have a porous solid which can be deformed due to the action of stresses like we have seen before. Here I'm making just a two-dimensional schematic, but this applies to 3 dimensions as well. Such stresses can produce a deformation of this solid as we have seen before. Let's say we apply a compression, then the solid will get smaller. But now also we have pores, and inside the pores we have pressure, a pressure which is applied by a fluid within the pores, and we're going to call it this pressure P. And this pressure P and the fluid within the pores can also cause a deformation, which might cause, for example, in this case, the pore to increase in volume. All right, so let's write down this new feature that we have, which are pores. Pores are going to be filled with fluids in the general case. It's just going to, the fluids are just going to apply a pressure which is a normal pressure on the walls. Fluids cannot apply a shear stress. So we're not going to have any shear stress applied from the fluids to the solids on the walls. Also, these walls are going to be deformable. So the pores are deformable now. And the walls of those pores are going to change the size. All right, so in order to get started, we're going to write down a few equations that will allow us to then write down and separate what contribution of deformation to the bulk volume comes from either the deformation of the porosity or the deformation of the solid part. All right, so the first equation I'm going to write is the volumetric strain. This is something that we have already seen. And in this chapter of pore elasticity, we're going to use this quite a bit. And just to make it shorter, I'm gonna call it with this epsilon. Let me write it again. And by definition, this volumetric strain is equal to the bulk volume, which here I'm going to call this differential omega, minus the original volume, this differential omega naught, divided the original volume. And I can work a little bit with this equation, just do some algebraic steps, and then I can write the bulk volume to be equal to 1 plus the volumetric strain times the original bulk volume, where remember this is a bulk volume at any time, and over here we have the initial bulk volume or original bulk volume. And this is going to be my equation number 1. Okay, so since we have porosity now, we can just go ahead and define what porosity is going to be. But notice that this is not going to be trivial, and you're going to see why in a little bit. Let me come back here to my plot, and let's go with the definition of porosity. The previous one we already knew, volumetric deformation. Let me just write it down, just for the sake of completeness. All right, so now let's go with porosity. Porosity at any time, let's say at a time t, after it deforms, I can define it as the ratio of the voids, and let's do this definition just with a schematic. So here with this empty rectangle, I mean the pores, divided the total bulk volume, which is the solid and the pores. This is the definition of porosity. Probably there is nothing new to you now, but you will see that we really need to be very specific about how we define this porosity, because that's going to have a great impact later on. Okay, when I define this porosity at any time, that's what is generally called as the Eulerian porosity. And it is valid at any time where these two sections, the porous section and the solid section, they are measured at that specific time. All right, so keeping that in mind, I'm going to make now a new definition. And this definition is going to be the definition of the Lagrangian porosity. And for example, if I wanted to write what the pore volume is according to the Eulerian porosity, I would say that the pore volume is equal to the porosity, Eulerian porosity, times the bulk volume. This is what we have from our definition before. This is definition 2. And what I'm going to do now is to define something which is called the Lagrangian porosity. And the Lagrangian porosity is going to be defined by this equivalency, where the pore space is going to be equal also to the Lagrangian porosity times the original bulk volume. So notice that these two bulk volumes, they are not the same, right? This one is at the time t in the form configuration. This one is at the time 0 or initial time without deformation. And notice that that is also linked to the volumetric deformation. All right, so from here, from this equation, I can derive that the Eulerian porosity is going to be equal to the Lagrangian porosity is going to be equal to the Eulerian porosity times the ratio of the bulk volumes at the deformed configuration divided the initial configuration. And this is going to be my equation number 2, and phi is going to be what I call the Lagrangian porosity. All right. Notice that this porosity that we have defined now depends on the initial volume. And this is very similar to what we have done before with mechanics. If you remember, whenever we calculate a strain, we link that to the original shape or to the original volume. And in this case, the porosity that we're going to use in the theory of porous elasticity is also linked to the initial volume. And it's more than just a geometric definition like the one of Eulerian porosity, but it's also linking that to the mechanical process and to this mathematical definition in which it is related also to time because it's related to the initial configuration. All right, so now we have seen these two kinds of porosities, and we'll go ahead and make another definition. And we'll define what the solid strain is. The solid strain, by definition, is going to be, and I'm going to refer to this in terms of volumetric strain, the volumetric strain of the solid part is going to be equal to the volume of the solid part at some time. So this superscript S means solid, minus the original volume of the solid part divided the original volume of the solid part. And this one again is a definition. I can do a little bit of math and also see that I can write the volume of the solid part at any time as a function of the strain, volumetric strain of the solid part, and that multiplied the original volume of the solid part. So here the solid part is in the case of the rock, just the mineral itself. And the deformation of the solid captures the deformation of the mineral and not the deformation of the entire thing. We're going to see that those two things are different. For example, this volumetric strain is a bulk volumetric strain. And that bulk volumetric strain refers to the entire solid. The solid volumetric strain, on the other hand, refers just to the deformation of the solid part. This is going to be a little bit more evident in the following equations that we're going to write, where we are going to have a better idea about what those are and how they contribute to the total deformation. All right, so this is going to be my equation number 3. And what I'm going to do is I'm going to combine 1, 2, and 3 in order to get to the equation, which is the micromechanical equation that links the bulk strain to the solid strain and to the porosity strain. And in order to get there, what I'm going to do is, let me rewrite this equation number 3. But basically, I'm just going to combine 1, 2, and 3. And let me find that. My mouse is a little bit lost. Okay, so here's my mouse. So this equation, I'm going to rewrite the equations using the definitions of Eulerian porosity and Lagrangian porosity. I can write the volume of the solid part at any time to be equal to 1 minus porosity, the bulk volume of the entire solid, right? So 1 minus porosity, that's going to be the solid fraction. The solid fraction times the bulk volume gives me the solid volume. And this one is gonna stay the same. And the solid volume in initial conditions, now this one is going to depend on the Lagrangian porosity, and this is going to be 1 minus the Lagrangian porosity at initial conditions times the bulk volume at initial conditions. All right, so at the end of the day, what I want to do is to obtain an equation that links all of these strains with the previous definitions I did before. So I'm not going to show all the steps that you need in here, but it's just basically just math. And combining these three equations, what we're going to obtain is that the volumetric strain of the bulk solid is a volume average of the strains of the two components or our two phases. This is going to depend on the strain of the solid. And notice that 1 minus porosity is the fraction of the solid plus the porosity strain. So probably this is the first time that you hear this term, porosity strain. And this is going to be equal to the porosity at some time, T, minus the initial porosity, divided the original porosity, times the porosity at initial conditions. And this is going to be our, as I was telling you, it's the micromechanical equation that links the bulk strain. Let me write that over here. This term over here is bulk volumetric strain of the entire porous medium. Over here I have the solid volumetric strain, and here I have the porosity strain. Actually, let me just to respect the order of these equations, let me change this and write it like this. Okay. So this term over here is going to be the porosity strain. And notice that it does look like a strain because it's the porosity minus initial porosity divided the original porosity. All right, so now that we have this equation, you may also question yourself, why are you keeping this initial porosity in the two terms? And actually, we don't have to keep it, but I just wanted to make this equation quite clear, that it is a volume average because it is linearly proportional to the volume fraction. So the more solid strain you have, that's going to be affect the volumetric strain proportional to the amount of solid, 1 minus porosity. And the same the porosity strain. The porosity strain is going to be linked to the amount of porosity. And I can rewrite this equation as, in a simpler way, as 1 minus porosity. This part stays the same. Let me change this epsilon, plus bar phi, where I already took care of eliminating these two porosities, and where this phi by definition is equal to the porosity minus the initial porosity, and also called change of porosity. Okay, so let's see what this is useful for. And in order to do that, we're going to see two examples that are going to help illustrate why this equation is important. And we're going to apply two thought experiments. So first we're going to have test number one. And in test number one, we're going to have our porous solid, and we're going to have pores over here. Imagine that these pores are connected. Okay, this is kind of difficult to make a schematic in 2 dimensions, but the assumption is that all of these are connected. And I'm going to apply a pressure to the pores so that the pores are going to expand. There's going to be pressure P. And because the porosity is connected, the pressure is going to be the same everywhere. All right, what would you think it would happen if we apply a pore pressure in this solid? You cannot really answer this until we add one more condition. And in this case, in test number one, we're going to fix the boundaries of this solid so it cannot contract or expand. And this is going to be done through these displacement boundary conditions. All right, if the solid cannot expand and I pressurize it inside, what I'm going to have is an increase in porosity, right? Because this is a deformable solid and the pore size is going to increase. However, because I have fixed all the conditions around the porous solid, the bulk volumetric strain of the porous solid is going to be actually equal to 0. That's because I'm setting these boundary conditions. And if this is true, that means that the equation that I have above is going to be the following. 0 bulk volumetric strain is going to be 1 minus initial porosity, volumetric strain of the solid part plus the change of porosity. And since this is 0, I can get from this equation that the volumetric strain is going to be equal to minus the change of porosity divided 1 minus the initial porosity. So let's try let's try to understand what this means. If I apply pressure, then the porosity would increase, right? And if the porosity increases, that means, according to this equation, that the porosity is going to be higher than 0. And since this number is going to be higher than 0 too, that means I'm going to have a negative volumetric strain. And actually that means a contraction. And that kind of makes sense, because that's what you would expect if you don't let the solid expand and you increase the porosity in the solid by increasing the pressure. All right, so there is something very important that I mentioned over here, and this is that we are going to assume when we work with the theory of pore elasticity, and also in order to follow the convention done by Olivier Cussy in his book, that we're going to follow the mechanics convention, the general mechanics convention, in which compression and contraction are negative and dilation and tension are positive. All right. So I hope that experiment was clear enough in order to illustrate what happens in this case when we just apply a pore pressure and we don't let the solid change volume as in bulk conditions. And notice that the volumetric strain in the solid comes at the expense, or let me rephrase that, the change of porosity comes at the expense of the compression of the solid part. Let's see another test that is going to help us also understand a little bit better the equation that we have over here. Okay, and what we're going to do now in this test is to the same porous solid with connected porosity, we're going to apply a stress and a pressure too, but with different boundary conditions. And these are the boundary conditions I'm going to apply. Now I'm going to apply stress. It's going to be the same in all directions. But look what I'm going to do. Simultaneously, I'm going also to apply a pressure. And this pressure is going to be such that, let me finish this plot over here. And this plot is getting a little bit difficult. Let me zoom in and finish it up. Okay, so simplify this a little bit. I'm going to apply a pressure within the pores to a value that when I apply the pressure, I do not let the pores change size. Okay, so wait, my screen is not doing what I want. Okay, now this is better. All right, so after applying stress, then I also simultaneously apply a pressure, and the volume of the pores is not going to change. So what's going to happen, and how I can relate the two strains? Well, let's use the equation that we have in this case, now opposite to what I had before. Now my change of porosity is going to be 0. And if the change of porosity is equal to 0, that means that the strain of the solid part is going to be proportional to the strain or the bulk strain divided 1 minus the initial porosity. So for example, let's try to put some numbers into this. If you were to apply a 10% strain on a porous solid and you don't let the pores shrink, and let's say that we have a 10% porosity, then the strain of the solid part will be 10% divided 0.9. So that means it's going to be higher than 10%. Why? Because although the bulk strain was 10%, the strain of the solid part is going to be actually higher because we're not deforming the pores. There is volume inside the porous solid which is not deforming. And in this case, not letting the porosity deform is going to come at the expense of more deformation of the solid. All right, so these two experiments are meant to highlight the role of the solid deformation and porosity deformation on the bulk volume deformation, because the two of them are going to participate in defining that bulk volume strain. All right, so with these basic definitions, we are ready to start working on to the following equations of poroelasticity that are going to allow us predict what change of porosities are and also what is the law that governs the deformation of a porous solid in terms of the Biot effective stress.